Inconsistency in torque between the coil and bushing connections can indeed cause resistance from phase to vary in a transformer. This is primarily because the torque applied to the connections directly impacts the tightness and quality of the electrical connection. A loser connection, resulting from insufficient or inconsistent torque, presents a higher resistance compared to a properly tightened connection. The examples provided clearly illustrate this effect. When the torque on the connections was inconsistent across different phases, the resistance between X12, X23, and X13 exhibited variations. Specifically, when the torque varied from phase to phase, the resistance also varied by approximately 0.7 ohms. Similarly, when the torque was inconsistent between the bushing and the coil connections, the resistance varied by about 0.2 ohms. While these resistance variations may seem small, they can be significant, particularly in high-power applications where even minor increases in resistance can lead to substantial power losses and heat generation. A high-resistance connection acts as a bottleneck for current flow, causing energy to be dissipated as heat. This overheating can degrade the insulation and other components of the transformer, potentially leading to premature failure. Therefore, maintaining consistent torque on all connections within a transformer is crucial for ensuring optimal performance and longevity. Properly torqued connections minimize resistance, reduce power loss, prevent overheating, and ensure reliable operation. To achieve consistent torque, it is essential to use a calibrated torque wrench and follow the manufacturer's recommended torque specifications for each connection type. It is also important to inspect the connections regularly and retorque them as needed, especially in environments subject to vibration or temperature fluctuations. The phenomenon observed relates directly to the principles of electrical contact resistance. Contact resistance is the resistance to current flow that arises at the interface between two conductors. This resistance is influenced by several factors, including the materials of the conductors, the surface finish of the conductors, the contact pressure between the conductors, and the presence of any contaminants or oxides on the surfaces. In the case of transformer connections, the contact pressure is directly related to the applied torque. Insufficient torque results in lower contact pressure, leading to a smaller contact area and increased contact resistance. Conversely, excessive torque can damage the conductors or the connection hardware, also leading to increased resistance or even mechanical failure. The ideal torque level provides sufficient contact pressure to minimize contact resistance without causing damage. Furthermore, the consistency of torque across all connections is important because variations in contact resistance can lead to imbalances in current flow and voltage drops within the transformer. These imbalances can negatively affect the transformer's performance and efficiency, and can also create localized hotspots that accelerate degradation. In addition to torque, other factors can also influence the resistance of transformer connections. These include the cleanliness of the conductors, the presence of corrosion, and the quality of the connection hardware. Therefore, it is important to thoroughly clean and inspect all connections before assembly and to use high-quality hardware that is resistant to corrosion. Regular maintenance and inspection of transformer connections are essential for preventing resistance issues and ensuring reliable operation. This includes visual inspection for signs of corrosion or damage, as well as periodic testing of connection resistance using a micrometer. If high resistance is detected, the connection should be disassembled, cleaned, and retorqued according to the manufacturer's specifications. Here's a more detailed breakdown of the factors influencing transformer connection resistance. Firstly, torque, as discussed, is the primary factor. Proper torque ensures adequate contact pressure, minimizing resistance. Secondly, material compatibility. Using dissimilar metals in connections can lead to galvanic corrosion, increasing resistance over time. Thirdly, surface condition. Clean, oxide-free surfaces are essential for low-resistance connections. Fourthly, connection hardware. High-quality connectors and fasteners designed for the specific application are crucial. Fifthly, environmental factors. Exposure to moisture, chemicals, or vibration can degrade connections and increase resistance. Sixthly, temperature. Temperature fluctuations can cause expansion and contraction, loosening connections over time. Seventhly, current carrying capacity. Overloading connections can lead to overheating and increased resistance. Eighthly, installation practices. Proper crimping, soldering, or bolting techniques are essential for reliable connections. Ninthly, maintenance. Regular inspection and retorquing of connections are necessary to prevent resistance issues. And tenthly, standards and codes. Adhering to relevant industry standards and codes ensures safe and reliable connections. To further elaborate on the effects of inconsistent torque, consider a three-phase transformer with connections X12, X23, and X13. If the torque on connection zone is significantly lower than the torque on connections X2 and X3, the resistance between X12 and X13 will be higher than the resistance between X23. This difference in resistance can cause an imbalance in the current flow through the transformer windings, leading to unequal heating and reduced efficiency. In extreme cases, the imbalance can even cause the transformer to trip offline or fail completely. Similarly, if the torque on the bushing connection is different from the torque on the coil connection for a particular phase, the resistance of that phase will be different from the resistance of the other phases. This can also lead to imbalances in current flow and voltage drops affecting the transformer's performance. To prevent these issues, it is important to use a calibrated torque wrench and follow the manufacturer's recommended torque specifications for all connections. The torque wrench should be calibrated regularly to ensure accuracy. It is also important to use the correct type of lubricant in the threads of the fasteners to achieve the correct torque. The lubricant reduces friction and ensures that the fastener is properly tightened. In addition to using a torque wrench, it is also important to visually inspect the connections to ensure that they are properly seated and that there are no signs of damage or corrosion. If any problems are detected, the connections should be disassembled, cleaned, and retorqued. Regular maintenance and inspection of transformer connections are essential for ensuring reliable operation and preventing costly failures. This includes periodic testing of connection resistance using a micro-ohmmeter. A micro-ohmmeter is a specialized instrument that is designed to measure very low resistances, typically in the micro-ohm or milli-ohm range. It uses a full wire measurement technique to eliminate the effects of lead resistance and ensure accurate readings. When testing transformer connections, the micro-ohmmeter should be connected to the 2 points between which the resistance is to be measured. The instrument will then inject a small current through the connection and measure the voltage drop across it. The resistance is calculated using Ohm's law. Resistance equals voltage divided by current. The measured resistance should be compared to the manufacturer's specifications or to historical data to identify any potential problems. If the resistance is significantly higher than expected, the connection should be investigated further. In some cases, it may be necessary to perform a more detailed inspection of the connection using infrared thermography. Infrared thermography is a non-destructive testing technique that uses an infrared camera to detect temperature variations on the surface of an object. High-resistance connections will typically generate more heat than low-resistance connections, so infrared thermography can be used to identify hotspots that indicate potential problems. The infrared camera captures an image of the object's surface, with different colors representing different temperatures. Hotspots will appear as bright areas in the image. If a hotspot is detected on a transformer connection, the connection should be disassembled, cleaned, and retorqued. In addition to torque, material compatibility plays a critical role in connection resistance. When dissimilar metals are used in a connection, galvanic corrosion can occur. Galvanic corrosion is an electrochemical process that occurs when two dissimilar metals are in electrical contact in the presence of an electrolyte, such as moisture. The more active metal will corrode preferentially, leading to increased resistance and eventual failure of the connection. To prevent galvanic corrosion, it is important to use compatible metals in connections or to use a suitable corrosion inhibitor. For example, aluminum connectors should be used with aluminum conductors, and copper connectors should be used with copper conductors. If it is necessary to use dissimilar metals, a corrosion inhibitor can be applied to the connection to prevent corrosion. The surface condition of the conductors is also an important factor in connection resistance. Dirty or corroded surfaces will have a higher resistance than clean, oxide-free surfaces. Therefore, it is important to thoroughly clean the conductors before making a connection. This can be done using a wire brush or a suitable cleaning solvent. After cleaning, a corrosion inhibitor can be applied to the surfaces to prevent future corrosion. The quality of the connection hardware is also critical for ensuring low resistance and reliable connections. High-quality connectors and fasteners are designed to provide a secure and reliable electrical connection. They are also typically made from corrosion-resistant materials to prevent corrosion. When selecting connection hardware, it is important to choose components that are designed for the specific application and that meet the relevant industry standards. Environmental factors such as moisture, chemicals, and vibration can also degrade connections and increase resistance over time. Moisture can promote corrosion, while chemicals can react with the metals in the connection, leading to degradation. Vibration can loosen connections, increasing resistance. To protect connections from environmental factors, it is important to use appropriate enclosures and sealing materials. Enclosures provide physical protection from moisture and chemicals, while sealing materials prevent moisture from entering the connection. Vibration-resistant connectors and fasteners can also be used to prevent loosening. Temperature fluctuations can also affect connection resistance. When the temperature increases, the metals in the connection will expand, which can loosen the connection and increase resistance. Conversely, when the temperature decreases, the metals will contract, which can tighten the connection and decrease resistance. To compensate for temperature fluctuations, it is important to use connectors and fasteners that are designed to accommodate thermal expansion and contraction. These components typically have spring-loaded mechanisms that maintain constant pressure on the connection, regardless of temperature. Overloading connections can also lead to overheating and increased resistance. When a connection is overloaded, it will generate more heat than it is designed to dissipate. This can cause the connection to overheat, which can damage the insulation and other components. Overheating can also accelerate corrosion and degradation, leading to increased resistance. To prevent overloading, it is important to ensure that the connection is properly sized for the load that it will be carrying. The current carrying capacity of the connection should be greater than the maximum current that will flow through it. Proper installation practices are essential for ensuring reliable connections. Improper crimping, soldering, or bolting techniques can result in high-resistance connections that are prone to failure. Therefore, it is important to follow the manufacturer's instructions carefully when installing connections. Crimping is a technique that is used to create a secure electrical connection between a conductor and the connector. A crimping tool is used to compress the connector onto the conductor, creating a tight mechanical and electrical connection. Soldering is a technique that is used to create a permanent electrical connection between two conductors. Solder is a metal alloy that is melted and flowed into the joint between the two conductors. When the solder cools, it solidifies and creates a strong electrical connection. Bolting is a technique that is used to create a secure electrical connection between two conductors using bolts and nuts. The bolts and nuts are tightened to a specified torque to ensure that the connection is properly seated. Regular inspection and retorquing of connections are necessary to prevent resistance issues. Connections can loosen over time due to vibration, temperature fluctuations, and other factors. Therefore, it is important to inspect connections regularly and retorque them as needed. The frequency of inspection and retorquing will depend on the specific application and the environmental conditions. Adhering to relevant industry standards and codes ensure safe and reliable connections. Industry standards and codes, such as those published by the National Electrical Code or NEC, provide guidelines for the design, installation, and maintenance of electrical systems. These standards and codes are designed to ensure that electrical systems are safe and reliable. By adhering to these standards and codes, you can minimize the risk of electrical hazards and ensure that your connections are properly installed and maintained. In summary, inconsistent torque, material incompatibility, surface contamination, poor connection hardware, environmental factors, temperature variations, overloading, improper installation, and inadequate maintenance can all contribute to increased resistance in transformer connections. Addressing these factors through proper design, installation, and maintenance practices is essential for ensuring reliable and efficient transformer operation.